Hello everyone, welcome to today's session. In my last class I discussed on sharpening spatial filters. So under that today I am going to discuss on unsharp masking and high boost filtering. Okay, this process is used for many years in printing and publishing industries for sharpening the images. And in this method, let us see how this method works here. Okay, so first of all, here in this method the original signal is first blurred. That is, we will perform smoothing on the original signal. So this is the original signal which is having sharp intensity transition, and we are going to blur this signal and we will smoothen these sharp intensities. And then this blurred image is subtracted from the original image, and the resultant is the unsharp mask. That is what you are seeing in figure C. So this is unsharp mask, and again this unsharp mask is added with the original signal in order to obtain the sharpened image. So this is how we produce a sharpened image in this particular process. Okay, so let me repeat once again. Okay, here in this process first the original image is blurred and the blurred image is subtracted from the original image, and the resultant image is the unsharp mask, and this unsharp mask is again added with the original image in order to obtain the sharpened image. So here the sharp intensity transitions are sharpened. Wherever you have the sharp transitions, at that particular point it is being enhanced. The image is enhanced by sharpening the image. So this is how we perform sharpening in this particular process. Okay, so now we can also develop an expression for sharpened image here. So first let me say this original signal, let this original image be, let the original image be f of x comma y. Okay, and let this blurred image, this is f of x comma y, and let this blurred image be f bar of x comma y. Okay, and blurred image be f bar of x comma y. Okay, now the unsharp mask can be represented in the equation form as, let this be g mask of x comma y. Okay, and we know that this unsharp mask is obtained by subtracting this blurred image from the original image. Right, so this is equal to f of x comma y minus f bar of x comma y. Original image minus blurred image produces unsharp mask, that is g mask of x comma y. So this signal is g mask of x comma y. This is f bar of x comma y, and this is f of x comma y. Okay, so now to obtain the sharpened image, we can also represent this sharpened image in the form of equations. So the sharpened image is always the weighted sum of unsharp mask with the original image. So therefore the sharpened image is represented as g of x comma y, which is equal to, so this is the weighted sum of unsharp mask with the original signal. Original signal is f of x comma y plus, let that weight be k into g mask of x comma y. I call this as equation number 2. So this is the equation for sharpened image using unsharp mask. Okay, so now here k is the weight and it is always greater than or equal to 0. Okay, so if K is equal to 1, then this represents unsharp mask operation, unsharp masking. If K is greater than 1, then this represents high boost filtering. High boost filtering. And if K is less than 1, then this emphasizes the construction of unsharp masking. Okay, so this is how we perform unsharp masking and high boost filtering to sharpen the image using this procedure. And this is the equation which represents unsharp masking and high boost filtering depending on the value of K, and this performs sharpening operation. Okay. Now let me consider an example to illustrate this unsharp masking and high boost filtering. So here in this, look at this image. So the first image is the original image and the second image is the result of blurring the original image, result of blurring the first image, and the third is the unsharp mask which is obtained by subtracting the blurred image from the original image. Okay, and now the result of unsharp mask when K is equal to 1 is shown in figure 4. Okay, and the result of high boost filtering when K is equal to 4.5 is shown in figure 5. Okay, so this is how we perform unsharp masking and high boost filtering, and this is shown with this example for different values of K. That is, for K equals 1 we have performed unsharp masking, and for K equals 4.5 we have performed high boost filtering here. So these are the results of this particular method. Okay, the last one is sharpening using first order derivative. First order derivative or non-linear for image sharpening and this is also called as the gradient. Okay, so here in my previous class we have discussed on the Laplacian. There we used the second order derivative for sharpening the image. Now here in this case we are using the first order derivative for sharpening the image, that we call as the gradient. So for the function f of x comma y, now for the function f of x comma y, the gradient of f at the coordinates x comma y can be represented as the column vectors, as the two-dimensional column vectors okay. So that is like this. The gradient of f is equal to gx by gy, which is equal to, we know that gradient is always equal to first order derivatives, that is dou f by dou x and dou f by dou y. This I call as equation number 1. And the magnitude of the gradient, the magnitude of the vector that is gradient of f is defined as m of x comma y and is given by, so magnitude of x comma y is equal to magnitude of the gradient of f, which is equal to square root of gx square plus gy square. So we know that the square root of a square can be approximately represented as m of x comma y is equal to magnitude of gx and magnitude of gy. You can approximate to this value, which I call as equation number 2. Okay, so now here using the gradient of f as well the magnitude of f, we can construct the mask for sharpening the images. So now let me consider the image, intensities of the image. Okay, so if this is f of x comma y, the center pixel is f of x comma y, then this is x minus 1, y minus 1, x minus 1 y, x minus 1, y plus 1. So this is equal to x comma y plus 1. So f of x plus 1, y minus 1, x plus 1 y, so now these are the intensities of the images which I have considered. Now let me consider the mask, 3 cross 3 mask. Okay, so to design the mask to sharpen the image using the gradient, first we need to consider this, and here we know that Z5, here the Z5 is nothing but f of x comma y, right? And now here to find out the magnitude of this gradient of f, first we need to find out the gradient of f, that is gx. So how do you find out this gx? So gx is equal to the first order derivative dou f by dou x. Do you remember the first order derivative equation? So dou f by dou x is equal to f of x plus 1 minus f of x. So this equation we have used in first order derivative, right? So using the same for the image f of x comma y, here this is equal to f of x plus 1 y minus f of x comma y. Okay, so now what is this from this image? So f of x plus 1 comma y is z8 and f of x comma y is z5. So this is equal to z8 minus z5, right? So now find out the gradient of y, that is dou f by dou y is equal to, now apply the same first order derivative equation for f of x comma y. This results with f of x comma y plus 1 minus f of x comma y. So what is f of x comma y plus 1 here? So this is equal to z6. So z6 minus f of x comma y is nothing but z5. So this is equal to z6 minus z5, right? So to find out the magnitude of this, so this magnitude m of x comma y is equal to magnitude of gx plus magnitude of gy from equation number 2. So substituting gx and gy, this results with magnitude of z8 minus z5 plus magnitude of z6 minus z5. So here I can construct the two masks, okay. So for gx, so mask for gx is equal to, so here z8 minus z5, z8 minus z5, so z8 is 1, z5 is minus 1 and remaining it is 0. This is gx, so that is the vertical mask. And for gy, so gy is nothing but z6 minus z5, z6 minus z5, so the mask is z6 is 1 minus z5, so minus 1 0 0, this is gy, so horizontal. So these are the mask, 2 cross 2 mask which can be used to sharpen the image using the first order derivative, okay. And here a person by name Robert proposes one more kind of mask which we call as cross gradient mask, okay. So Robert proposes cross differences, okay, that is for vertical and horizontal. For cross differences, here gx is equal to so for cross difference, so here for 2 cross 2 mask, z9 minus z5 and z8 minus z6. So this is equal to z9 minus z5 and gy is equal to z8 minus z6. Therefore, the magnitude of this is magnitude x comma y is equal to magnitude of z9 minus z5 plus magnitude of z8 minus z6. And these operators are called Robert's cross difference operator, okay. This is Robert's cross difference operator or cross gradient operator, and the mask generated by this is nothing but cross gradient mask. So for gx I can construct a mask like this, so which is equal to z9 minus z5. So z9 minus z5, z9 minus z5, so okay, this is for gx, and the another mask is z8 minus z6, z8 minus z6, so this is again the 2 cross 2 mask for gy. So these two are called cross gradient mask. Okay. So now here in these two types of mask, that is 2 cross 2 mask, there is no center symmetry. So to achieve center symmetry, we have to consider the mask of like odd masks we have to consider, which is having the center of symmetry. So the smallest odd mask what we can have is 3 cross 3 mask, okay. So Sobel proposes this kind of mask, that is the 3 cross 3 mask. So Sobel proposes 3 cross 3 mask, which is the smallest odd mask which can have a center of symmetry, okay. So which is equal to, so here gx is equal to, here it is like this, so z7 plus 2 times of z8 plus z9 minus z1 plus 2 times of z2 plus z3, okay. So here gy is equal to Z3 plus 2 times of Z6 plus Z9 minus Z1 plus 2 times of Z4 plus Z7. These operators are called Sobel's operator. Sobel's operators. Okay. So now let us construct the mask for these. So this is Gx. This is G1. So now look at this. Z7 plus 2 times of Z8 plus Z9. Z7 2 times of Z8 plus Z9. So 1 plus 2 plus 1 minus of Z1 2 times of Z2 plus Z3. Z1 2 times of Z2 plus Z3. So this is equal to minus 1, minus 2, minus 1. Remaining it is 0. Okay. So here for Gy it is equal to Z3, Z6, Z9, Z3, 1, 2 times of Z6, Z9 minus of Z1, Z4, Z7, Z1, 2 times of Z4 and Z7. So these are called Sobel masks. Okay. So the magnitude of this can be obtained by Z7 plus 2 times of Z8 plus Z9 minus Z1 plus 2 times of Z2 plus Z3 minus of Z3 plus 2 times of Z6 plus Z9 minus Z1 plus 2 times of Z4 plus Z7. Okay. So this is the magnitude of this mask. So this is how we can obtain the 2 cross 2 mask as well as the 3 cross 3 mask. Okay. And these masks are used to sharpen the image, and this can be done by using the gradient or the first order derivative. Okay. So these are the masks which we use to sharpen the images. This is all about sharpening spatial filters. Okay. And one more thing you need to remember is that in these type of filters, always the sum of mask coefficients is always equal to 0. Observe that here. The sum of mask coefficients is always equal to 0. It might be in 3 cross 3 or 2 cross 2. In all the cases, the sum of mask coefficients is equal to 0. Okay. So in this particular module so far we have discussed on spatial domain filters. Now let us move on to the frequency domain. Okay. So we know that the images can be processed using 2 principal domains. One is spatial domain and another one is frequency domain. So we have discussed on spatial domain, the filters used in spatial domain, how to sharpen or smoothen the images using spatial domain, all that we have learnt so far, right. So now let us understand the frequency domain. So here we know that in spatial domain we perform operations directly on the pixel present on the image plane, whereas here in frequency domain, first the original image is first converted into transform domain, that is the Fourier transform domain. Okay. Now we will process the image in this particular Fourier transform domain. Now here we will perform some processing operations in Fourier transform domain. Okay. And after performing these operations, again we bring back the results in original form. So for that we have to perform inverse Fourier transform. Inverse Fourier transform domain. So after performing inverse Fourier transform, the results are obtained in the form of original form. Okay. So here in frequency domain we know that we do not directly manipulate on each and every pixel present in the image. whereas the original image is first converted into transform domain, that is the Fourier transform domain, and we perform some processing operations on this particular Fourier transform domain image, and then we bring back the results into original form by performing inverse Fourier transform. So for this, in our previous semesters in subjects like signals and systems, we have studied Fourier transforms, Fourier series, all that we have learned. Fourier transform representations, equations, and all that we have studied for signals, and whereas here we are applying the same for images. There we were dealing with single variable, here we have two variables. That's the difference. Okay, let the digital image be f of x comma y. Okay, the Fourier transform of this image results with f of u comma v. Okay, now we will perform operation on this f of u comma v, and then the results are brought to f of x comma y by performing inverse Fourier transform. So that is f of u comma v can be discrete Fourier transform, and here f of x comma y. Okay, so this is how we perform operation in frequency domain. Here the digital image, that is f of x comma y, is converted into f of u comma y, that is the transform domain, by performing discrete Fourier transform, and this image can be brought back to the original form by performing inverse discrete Fourier transform. So now let us see the expressions for performing this. The two-dimensional discrete Fourier transform is given by f of u comma v, which is equal to summation x equals 0 to m minus 1, summation y equals 0 to n minus 1, f of x comma y into e power minus j 2 pi by m, u x into e power minus j 2 pi by n vy. This I call as equation number 1. Okay, so this is the discrete Fourier transform equation, and we have used for single variable in signals and systems. This is for two-dimensional, that is we are dealing with two variables here. Okay, so this is the formula for finding f of u comma v from f of x comma y, where f of x comma y is the digital image of m cross n samples. Okay, and u and v are frequency domain variables. And it ranges from, u ranges from 1, 2, 3 up to m minus 1, and v ranges from 0, 1, 2 up to n minus 1. Okay. To obtain f of x comma y from f of u comma v, then we have to perform inverse discrete Fourier transform. Okay. So inverse discrete Fourier transform Okay, that is f of x comma y is equal to 1 by mn summation u equals 0 to n minus 1, v equals 0 to n minus 1, f of u comma v e power j 2 pi by m ux into e power j 2 pi by n vy. Okay, so now these are the two formulas to perform discrete Fourier transform. Equation 1 is used to perform discrete Fourier transform, that is for converting the frequency domain image to Fourier domain, okay, and to obtain f of x comma y from f of u comma y, that is converting back to frequency domain from the Fourier domain, we use this inverse discrete Fourier transform formula, that is as shown in equation number 2. So these are the two formulas which we use very frequently here in this for performing all frequency domain filtering operations. Okay. Now let us understand the properties of two-dimensional discrete Fourier transform. Under this we have relationship between spatial and frequency intervals. So to illustrate this property, let me consider a continuous image in t and z direction. Let this continuous image be called as f of t comma z. So this is a continuous image which is in spatial domain. Okay. Now I will convert this continuous image into digital form by performing sampling and quantization. So let us say that this is some continuous image, whatever might be the image. So now I am going to digitize this image, okay, by performing sampling and quantization. Okay. So now this digitized image, or the image which is converted in digital form, I call as f of x comma y is the digital image having m cross n number of samples. That means here it has m number of rows and m number of columns. So m cross n number of samples it has. Okay. In the direction t and z. Okay. So now in order to understand the relation between spatial and frequency intervals, so let us consider the frequency domain variables. Okay. So the frequency domain variables u and v are represented by delta u is equal to 1 by m into delta t. This I call as equation number 1. And delta v is equal to 1 by n into delta z. This I call as equation number 2. Okay. So here this delta t and delta z represents the separation between the samples. So delta t and delta z represents the separation between the samples in t direction and separation between the samples in z direction. This is what is the interval between the spatial and frequency domain. So where represents the separation between the samples. Okay, so now this is the relation between the spatial and frequency intervals. That means delta t and delta z are in spatial domain, they are represented in spatial domain, and delta u and delta v are the frequency domain variables. So this is the relation between spatial and frequency domain intervals. Okay. So the second property is the translation and rotation. So here the Fourier transform pair satisfies this translation property. The Fourier transform pair satisfies the translation and rotation property and it can be represented as f of x comma y into e power j 2 pi into u naught x by m plus v naught y by n, which is equal to f of u minus u naught and v minus v naught. This I call as equation number 1. So multiplying a frequency domain image, that is f of x comma y, with an exponential as shown, shifts the signals by u naught and v naught. Okay. So for example, again, if f of x minus x naught and y minus y naught results with f of u comma v into e power minus j 2 pi into x naught u by m plus y naught v by n. This I call as equation number 2. Or multiplying this discrete Fourier transform domain image with the negative exponential shows the shift in x naught and y naught. Okay. So now this represents the translation property, and now here if at all you convert these pair into the polar coordinates form. So in polar coordinates this can be represented as, let x is equal to r cos theta, y is equal to r sin theta, and u is equal to w cos phi, v is equal to w sin phi. So substituting this in this expression, in this pair, then the result of this the result obtained is, so the result in polar form what we get is f of r plus theta naught, f of w phi plus theta naught. So simplifying that, equation number 3. So simplifying the above pair, Fourier transform pair in polar coordinates, this results with f of r comma theta plus theta and f of w comma phi plus theta. So what does it indicate is that if there is a rotation of the signal f of x comma y by an angle theta naught, then after transforming to Fourier domain, then also there is a rotation of the image by the angle theta naught. Okay, so by the same angle theta naught. Okay, so this means if f of x comma y is rotated by theta naught, then after converting into Fourier transform f of u comma y, then f of u comma y is also rotated by the same angle theta naught. So the next property is periodicity. The Fourier transform and its inverse are infinitely periodic in u and v directions. Okay, so the Fourier transform and its inverse are infinitely periodic in u and v directions. Okay, so for that consider f of u comma v, discrete Fourier transform signal. So this is equal to f of u plus km. So in signals and systems you have used this periodicity property and the equation of that periodicity property. The same here we are using, but it is with respect to two variables. Okay, so this is equal to k1m into y. So which is equal, into v, which is equal to f of u comma v plus k2 n, and this can be represented as f of u plus k1m v plus k2 n. This I call as equation number 1. So this is the property of periodicity. So the equation is based on that periodicity equation. Okay. So now similarly for f of x comma y, as I have told, the Fourier transform and its inverse both satisfies periodicity. Okay, both are infinitely periodic. Therefore this is equal to f of x plus k1m comma y is equal to f of x comma y plus k2 n. So this can be represented as f of x plus k1m and y plus k2n. This I call as equation number 2. Okay, where k1 and k2 are integers. Okay, so now in order to illustrate this periodicity, let me consider one-dimensional discrete Fourier transform signal. Okay, so let me consider a signal which is like this. Let me write it here. Okay, so now f of u. Okay, so this is 0, this is m, and this moment this is m, this is m minus 1, and this is two back-to-back periods meet here. This is m by 2, the very m by 2 minus 1. Okay. So now look at this one-dimensional discrete Fourier transform. So now this is a signal, discrete Fourier transform, one-dimensional signal. It is periodic, infinitely periodic. Okay, so now here I have considered the two periods. Okay, so this is one period and this is the second period, and this is the point where two back-to-back periods meet, and the sample duration is this, but 0 to m. But in this duration we do not have one complete single period. So to obtain that for this signal here, so f of x into e power j 2 pi u naught x by m, which is this I call as equation number 3. Okay, so now this is the equation or expression for this particular periodic signal. This is infinitely periodic. Now in order to obtain one complete period in this sample 0 to m, we have to shift this signal. So this shifting can be performed by multiplying f of x with minus 1 power x. Then the resultant signal is f of u minus m by 2. Okay, now u0, the shift is by m by 2. This I call as equation number 4. That means here the resultant signal is like this. Okay, so now here okay, so this is 0, m minus 1, this is m by 2. Now this is shifted by m by 2. Now here in this case, now we can obtain one complete period in this sample, that is 0 to m minus 1. Right. So now we can perform processing operation on this kind of images. Similarly, for two-dimensional discrete Fourier transform images, for if at all I consider two-dimensional discrete Fourier transform image, let me consider an example of that. So now consider this two-dimensional discrete Fourier transform image, okay, that is f of u comma v. Now here there are 4 periods, 1, 2, 3 and 4, okay, and this is the point where 4 back-to-back periods meet, these 4 periods meet, and the one square which I have written in bold is a data array of size m cross n. Okay, and this data array contains quarter samples in each period. So this contains quarter samples in each period. So by shifting this particular data array to one particular period, then all the samples lies completely in one particular period. Okay, so that can be done, that is in this fashion. So if this is shifted, this is the point. So again here as it is periodic, there are many periods which is present here in the image. So this is the point where 4 back-to-back periods meet. Okay, now here this data array f of u comma v, this lies in this period, that is all the samples lies in one complete period by shifting this. So to shift this particular Fourier transform two-dimensional image, so this can be done by f of this can be done by multiplying f of x comma y with minus 1 power x plus 1. So this results with f of u minus n by 2 comma v minus n by 2. So this is how you can shift the message in order to obtain all the samples in one complete period for performing processing operations on this particular Fourier transform domain image. Okay, so the next property is symmetry. So we know that any real or complex number or the sum of even and odd components or even and odd parts, right? So any real and complex functions or the sum of even and odd parts, that is w of x comma y is equal to w even of x comma y plus w odd of x comma y. This I call as equation number 1. But we know that the even parts are represented as w even of x comma y is equal to w of x comma y plus w of minus x minus y whole divided by 2. This I call as equation 2a. And w odd of x comma y is equal to w of x comma y minus w minus x minus y whole divided by 2. This I call as equation 2b. Now substituting these two, 2a and 2b in 1. Substituting 2a and 2b in 1, it results with identity. That is, w of x comma y is approximately equal to w of x comma y. I call this as equation number 3. Okay, that means they are symmetric, identity. But we also know that the even components are symmetric and the odd components are antisymmetric. Therefore, we know that the even components are symmetric and odd components are antisymmetric. Therefore, w even component of x comma y is equal to we of minus x minus y, and the odd component or w odd minus of, as it is antisymmetric, this can be represented as shown in 4a and 4b. So the even components are symmetric and odd components are antisymmetric, right? Therefore, we also know that the product of even and odd components are always equal to 0. Since it is symmetric and it is antisymmetric, so the product of these two nullifies and it results with 0. Therefore, the product of even and odd components are, so summation x equals 0 to m minus 1, summation y equals 0 to n minus 1, w even of x comma y into w odd of minus x minus y, which is equal to 0. So this is the symmetric property. Even components are symmetric, odd components are antisymmetric, and the product of these two is always equal to 0. It results with 0. This is one of the property of this two-dimensional discrete Fourier transform. So next, the last property is given by two-dimensional convolution. So the circular convolution of this two-dimensional discrete Fourier transform is given as the circular convolution of two-dimensional discrete Fourier transform is given as h of x comma y, which is equal to summation n equals 0 to n equals 0 to n minus 1 f of m comma n and h of x minus n and y minus n. This I call as equation number 1. Okay, so where here x is equal to 0, 1 up to m minus 1, y varies from 0, 1, 2 up to n minus 1. Okay, so we also know that the convolution in frequency domain is multiplication in Fourier transform domain, and the convolution in Fourier transform domain is multiplication in frequency domain. So to illustrate that, for two-dimensional convolution theorem is given as convolution of h of x comma y is equal to f of u comma v into h of u comma v. This I call as equation number 2. Conversely, f of u comma v convolution of h of u comma v is equal to f of x comma y into h of x comma y. This I call as equation number 3. So here this says that this is the frequency domain representation, this is transform domain representation. So the convolution of two images in frequency domain is equal to the multiplication of the images in Fourier transform domain, and the convolution of two images in Fourier transform domain is equal to multiplication in frequency domain. Okay, so this is the last property of this two-dimensional discrete Fourier transform. So this is all about the properties of discrete Fourier transforms. So in my next class, let us discuss on the frequency domain filters. Okay, thank you.